going to be a time here. The mass of carbon-13 can be determined by summing the mass. I didn't talk about this. You know, this is different. This test is different than your test is going to be. Your test is going to be. And do you remember in chapter 1? There's the law of conservation of mass, the law of conservation of energy, and the law of conservation of mass and energy. In chapter 1 this semester, I spent a lot of time talking about the law of conservation of mass and energy. Talked about that. The reason it had to be modified is because of this. And so this particular semester, I talked about this. Delta E is equal to mc squared. But, you know, last semester it didn't go so well. This whole delta E equals mc squared stuff, so I skipped it this semester. Didn't talk about it at all. This was part of the problem here. Why do we have to weigh these in a mass spectrometer, you might ask? Isn't it just as easy to just add up the masses? So, you know, why do you need to buy a $50,000 mass spectrometer when we know what carbon-12 or carbon-13 is made of? Carbon-13 consists of 6 protons, 7 neutrons, 6 electrons. Well, I know what a proton weighs. You know, what does a proton weigh? I know what a neutron weighs, and I know what an electron weighs. Proton weighs 1.0072 U. So this is 6 times 1.0072 U. Neutron is 1.08 U. Electron is 0.0005 U. Just add up the masses. But you know what? The masses don't add up. The masses don't add up because of the mass defect. And so I didn't talk about the mass defect this semester yet. We'll talk about it later. And so we're stuck. We can't add up the masses because there's something called the mass defect. We have to weigh these in a mass spectrometer. That's how we're going to get the mass. Okay, so going back to the test here. The answer is false. But don't worry about this for your test. Instead, you need to worry about this. I didn't do too many of these reactions on this test. I had them more on the next test and on the final. You're going to have more of these types of reactions. Be prepared for it. Spend most of the time talking about the reaction. Okay, what else?
I guess I'm just still confused about when we get an equation, how to tell if it's metathesis, acid base, or redox, like which one to do. Like I just don't really right off the bat get, like, are we supposed to just try them out, or?
You just try them out. Unless you recognize the pattern.
But like, what's the pattern? I think that's what I'm not really getting.
AB plus CD,
Yeah.
A plus BF. Those are 2 patterns that we covered. And so if we look at the first one, iron metal plus hydrochloric acid. Iron metal, iron solid plus hydrochloric acid. Does that look like an AB plus CD pattern? How about an A plus BF pattern?
Yes.
And this is an A plus BF pattern. And so that means it could be single replacement. Could be. But the thing is, I'm trying to get away from patterns and getting more towards a general approach to this. In a general approach, you just try it out and see what happens. So the general approach to this is you just forget about the pattern, because there's a lot of patterns to memorize and sub-patterns. Here's what I should show you. Here, what we try is metathesis first. And so what we do is we inventory the solution for metathesis. What do we have in solution? Iron. Does iron metal get torn apart? If you drop a chunk of iron in a cup of water, is the iron going to get torn apart and made into iron ions? No. You're going to have a chunk of iron at the bottom of your glass of water. Simply, this is a chunk of iron at the bottom of a glass of water. How about HCl? Does that get torn apart by water?
Yeah.
And then we also have water. Water, because it's aqueous here. And so what you do is you first look for metathesis. What are metathesis reactions? Ion combinations. What ion combinations do we have? H and Cl. How can you get H and Cl to come together? You gotta evaporate all the water. If you evaporate all the water, you'll force the H and Cl together because HCl is a strong acid. Water has no problem keeping those separate. So we try metathesis that failed. I'm getting away from patterns. So we look for ion combinations. Next we look for acid base. And so you go down the acid base chart. Iron's not on the acid base. H plus, acid. Cl minus, it's a base, but it's too weak, so it's called neutral. Water, the base. And so one potential reaction I see is this: H plus H2O yield H3O plus. But that's not really a reaction because H plus we already know is totally unstable, and when we see H plus, it really means H3O plus. And so this reaction is a little bit redundant. So it's not really. Do you see any other combinations of acid base that we could do? No. And so if it's not metathesis, no reaction, and it's not acid base, no reaction there, then what's left? Redox. And then we go through redox and see what potential redox reactions occur. And so instead of trying to fit it into a pattern, the problem with a pattern is that sometimes sometimes the things don't want to follow their assigned role. This is like if you have a whole bunch of pet dogs and you assign roles to your pet dogs. Okay, this pet dog is going to be very quiet, well behaved. Right? These are totally maybe arbitrarily assigned. This pet dog is going to be very violent and vicious. But you assign those roles, but you have to understand the nature of the species you're dealing with. What if you misassign the roles? What if you assign the very sweet dog role, putting the vicious dog in there? Is it going to work out so well? No. And so this is the problem with the patterns. The patterns is you're making some assumptions about it. Whereas if we don't follow the pattern, this is what I was doing. You don't follow the pattern, what do? We just assign this iron to reducing agent. H plus, an oxidizing agent. Chloride is a reducing agent. Water is both an oxidizing agent and a reducing agent. What's the strongest oxidizing agent? H plus or water? What's a better oxidizer? You don't even need the chart for this. What's a better oxidizer? H plus, acid, or water? H plus. In other words, oxidizers would do what? Oxidizers take electrons from things like metals. Oxidizers are more reactive. So which one's more reactive? Drinking a glass of acid or drinking a glass of water? I would rather drink a glass of water because it's more stable, it's less reactive. But if I'm trying to dissolve metal, I probably wouldn't try to dissolve my chunk of iron in water. I'd probably try to dissolve my chunk of iron in acid because it's more reactive. As far as reducing agents go, what's better, reducing agent? In other words, what do you think is easiest to burn? You know, paper is pretty easy to burn. So paper is not on one of these. Is it easy to burn water? Have you ever tried to burn table salt? Will a table salt ignite? And table salt will cause a flame to turn yellow, but does it ignite itself? No. If you tried to build a fire, let's say you ran out of firewood, but you have a bottle of salt, and you tried to use a bottle of salt to generate heat from a fire, it's not going to work. That's because chloride is such a bad reducing agent. That's because oxide is such a bad reducing agent. But what about iron? In the Boy Scouts, my dad was in the Boy Scouts when I was young. In the Boy Scouts, do you know how we started fires? We got a wood stick and a piece of wood like this, and then we used steel wool. Do you know what steel wool's made out of? Iron. So we put a piece of steel wool between the wood stick and the wood, and then do this until the steel wool caught on fire. And once the steel wool caught on fire, then that would ignite the wood, and we'd have a little fire going. And so we used iron all the time to ignite fires, campfires. And so iron is a pretty good reducer. In fact, if you buy a bottle of powdered iron, and you read the label, I don't know if you like to read the label, but let's take a look. Powdered iron label. Warnings. You see with this red number 4? You know what that red number 4 means? Well, the red number 4 means fire hazard. And 4 is the worst you can get. And so let's look. These are NFPA signs, NFPA labels. So let's look at the NFPA label red. The scale goes from, where does it go? 0 to 4, where 4 is the worst. Red denotes flammability. Iron is flammable. This is why you gotta watch out for explosions of iron. Why? Because it's a good reducer. All metals, not all. Is gold really flammable? Platinum? No. Anyway, like I said, you do not need to know chemistry. All you need to know is how to use this chart. Where did I put it? I have too many open tabs. All you need to know is how to use this chart. And so what's the strongest reducer here? Lithium. Lithium is highly flammable. You got to watch out. Lithium fires are extremely nasty. Lithium fires are extremely difficult to put out. You do not put out metal fires using water. Why? You would never put out or try to put out a lithium fire using water. You know why? Because water is an oxidizer. Is it a very good oxidizer? No, it's a bad oxidizer, but lithium is such a powerful reducer, it doesn't matter. Water. So what happened, apparently this is a hearsay because I didn't actually read the report, but there's a battery factory in Japan that was completely burnt to the ground. And apparently the first fire personnel on scene tried to put out the fire with water and caused an even bigger explosion in the fire. Because they're spraying water, which is an oxidizer on lithium, they're gonna cause trouble, big trouble. In fact, water would be, you know what these 3 dashes mean here? Yeah, water goes here. So water should be able to oxidize aluminum, magnesium, sodium, calcium, potassium, and lithium. So you don't want to use water on any of these. And at high temperatures, you don't want to use water on any metal fire. You know, if you have a metal fire, you got to use some other agent, not water. And so when you read the warning on metal bottles, it says, do not use water without the fire. So anyway, lithium is the best, and then out of these ones, where does iron, chloride, and water exist? So lithium is the best, so let's go on up here. Iron is good. Iron's a good not oxide, iron's a good reducer. And then we have chloride and water. If you go up the chart, see water. Water's not so good. Chlorides is even worse, it appears to be. And so that's it. The oxidizer is the same thing. We could look. You know, H plus is a pretty decent oxidizer. Water is a pretty bad oxidizer. And so the thing is, we do this. The likely reactions would be iron and H plus. And we copy the reactions down here. 2H plus 2 electrons yields H2 gas. Where did I get that? I just copied it down. Here's H plus. 2H plus puts 2 electrons yields H2. And then I look for iron. Iron, I have to reverse it because iron's not a product, iron's a reactant. So flip this equation. So iron as a reactant goes to iron 2 as a product. So iron as a reactant goes to iron 2 as a product plus 2 electrons. And then we add it. Just so happens 2 electrons, that balances quite nicely. And so what we're going to get is this. We're going to get iron solid plus 2H plus yields iron 2 plus H2 gas. This is the NIE. What we do is, in this case, we just get the NIE if we use the chart method. If we use the single replacement method, we'd get the CE, then we do the IE and the NIE. Now we got to figure out if the driving force is present. And so this is the oxidizer. If this is the oxidizer, then on the opposite end must be the reducer. These are conjugates. And this is the reducer, so on the other side of the equation, this must be the oxidizer, as far as the conjugate relationship goes. And so this is our reducing agent, this is our oxidizing agent. Iron 2 is our oxidizing agent going backwards, and H2 going backwards is our reducing agent. And then we compare the two oxidizers. Which one's stronger, H plus or iron 2? Here's iron 2, here's H plus. It looks like H plus is a stronger oxidizer than iron 2. H plus is stronger, iron 2 is weaker. That means iron must be a stronger reducer than hydrogen, and we can confirm it there. Iron is a stronger reducer than hydrogen. And, this would be the equation here. The driving force. Now, if you know some patterns, you might be able to do this faster. You might be able to do this faster, but it's dangerous. You might be able to do this faster recognizing that this is single replacement. This is A plus BX. But if you recognize this as being an A plus BX, then you have to make sure that each species will play its proper role. What's the role assigned to A? A should be the reducer. And so when we look at this, there's going to be water present as well. So if A is the reducer, we look iron. Well, that's a good start because iron's a pretty decent reducer, but is there a better reducer? Well, we have chloride and water, so it looks like iron's good. And then B's got to be the oxidizer. So H plus is the oxidizing agent. And H plus is a decent oxidizer. Is water a better oxidizer? No. Is iron a better oxidizer? No. Is chloride a better oxidizer? No. And then X is spectator. Is chloride stable, unreactive? Yes. And so everybody's going to play their role. If everybody plays the correct role, then we're good. We can solve this using single replacement. Using single replacement, this is going to give us iron 2 or iron 3 chloride. Which one will it be? Iron 2 or iron 3 chloride?
Iron 2.
Iron 2. And hydrogen. And then we look at it differently. We go from activity, so iron versus hydrogen, which one's more active? Well, which one's the most active on the periodic table? Or on this chart, which one of these is most active? Lithium. And so we'll compare the activity of iron versus hydrogen. Iron's more active. And so for single replacements, we say the driving force a little differently. We call this more active. This is less active element. We compare the two elements. This is the driving force here, and we need 2 HCl to balance it. This would be the CE, and then we do the IE. The IE, do we dissociate, break apart, do anything to iron and water? Nothing happens. HCl in water? Breaks apart, 2 H pluses, 2 Cl minuses. FeCl2 in water. Does it break apart in water? Yes. Fe2 plus 2 Cl minus. H2, does it break apart in water? H2 gas? No, it just bubbles out of gas, out of the water as a gas, effervesces. And so what's the spectator here? The chloride. Well, that's the role it was supposed to play. Good. The reducer is iron solid. The oxidizer is a 2H plus. This is going to form iron 2 and H2 gas. And so we could have done this single replacement. If we did this single replacement, we generate the CE, the IE, and the NIE. If we do this using the chart method, we just go straight to the NIE. All right, so how do you know which one it is? Well, how you know is you don't have to know, right? You just try them all. We always try them all. For example, you know, today somebody asked me, you know, a lot of people want to come up with very broad statements. So somebody asked me, if you have an acid plus an acid yields what? Acid plus acid. And so they said, well, an acid plus an acid is going to yield no reaction because both are acids, so acids want to do the same thing, there's going to be no reaction. And so you could mix an acid and an acid and nothing's going to happen, whereas if you mix an acid with a base, something's going to happen, right? Because both acids want to give up hydrogens. If both acids want to give up hydrogens, then who's going to take it? Nobody. And so that's what we call compatible chemicals. When you store chemicals on the shelf, you got to make sure you don't store them together. So for example, if you have powdered aluminum and powdered rust, you want them stored together? If you take powdered aluminum and powdered rust, you don't store them together because rust is an oxidizer, aluminum is a reducer. If those happen to get mixed, what's going to happen? Thermite. You know, you're going to have thermite. And so we try to keep things compatible. And so I don't know why this question came up, but you know, they're asking about. And then I said, no, because you're only looking at one type. How many types of reactions are there?
3 types.
Yeah, there are 3 types of reactions. So yeah, sure, acid, I expect nothing to happen. You're safe. But we aren't looking just at acid. What else are we looking for? Metathesis and redox. Okay. And so just because nothing happens in the acid sense doesn't mean nothing's going to happen. And you know, I could give you examples of stuff where, you know, something happens, like if I take a look at these 2 acids, these are 2 acids, wow, 2 acids. Nitric acid and hydrochloric acid, both of them are strong acids, right? Both of them are strong acids, well, both of them want to do the same thing, so maybe it's a compatible mixture. But no, it's not. And so what would you look for first? You'd look for metathesis, right? This is AB plus CD. AB plus CD yields same thing, no reaction. Then you'd look for acid base. Probably the only acid base reaction is this, H plus and water. When you inventory this is going to be the strongest base present, water. What's it going to form? Hydronium, but that's a bit redundant because H plus and hydronium we're using interchangeably. H plus is very reactive. So this, and that leaves us with redox. And in this particular case, you don't want to mix these two acids together because that's a redox reaction that occurs here. There's a redox reaction. Well, is that a single replacement redox?
Nope.
No. And so how do we do it? How do we figure out the redox reaction? Chart method. So this one works with the chart method. Does that answer the question about how to figure out the reactions?
So when we inventory, do we need to include H2O
Yeah.
for the IE?
We always have. When we inventory, we always have to include H2O.
Or like acid reactions or like things that have aqueous solutions in them, right?
Yeah, unless they're all solids. Like when I inventory thermite, there's no H2O present. So we can't include H2O. Yeah, it'd be different. We have to look at a different, we have to make some kind of compromise. Because when I look at iron 3, where is iron 3 on this? I have to make some kind of judgment. Because the iron 3 ranking here is for iron 3 AQ. But if I have iron 3 locked in a lattice, then it's going to make it less reactive than iron 3 free in aqueous solution. And so I have to make some adjustments here. But we're not going to get into that much detail. We're just going to say, yeah, it's a pretty decent oxidizer. In fact, it's a really good oxidizer. Iron 3 is a great oxidizer. When you look at this chart. So the thing about the patterns is in Chem 4, on our memorization list, my supplement doesn't have it, but there's a whole bunch of these patterns that we memorize. In single replacement, we have the patterns A plus Bx, where Bx is a salt. A plus Bx, where Bx is a weak acid. A plus Bx, where Bx is a strong acid. A plus Bx, where Bx is water. A plus Bx, where A is what we call, the superactive metals. And if you go back to the PowerPoint, you can see it. And so, if I go back to this PowerPoint, the chemical reactions PowerPoint 1. It's in your supplement. Did you see all those? Yeah, so that's one way, but I'm trying to avoid that way because it's too much work and too much memorization. And so we have a more generalized approach. You're fine without even knowing the single replacement method. You'd be fine just using the chart method for everything. And so, we inventory. When we inventory, let's say this one on the left, we got to include water. Because these are aqueous solutions. We got H plus, nitrate, iodide, and water. And then we use the chart. We don't have to memorize what these are, but you have to be very careful when you use the chart because H plus is an OA And then nitrate's an OA, but nitrate requires H plus together, and that's an OA. And then iodide's an RA, and water's an OA and an RA. And then we pick the strongest OA. The strongest OA is nitrate, sure. Strongest RA is iodide. And then there's a reaction that occurs. Even though it looks like no reaction occurs. Does that answer?
Yeah, yeah.
You gotta, the best thing is this. You know what we were doing earlier with, whenever you're uncomfortable with something, you have to generate some familiarity with it. And so what I do is this. Oops, I didn't want to do that. Do this. What I do is I just go through a whole bunch of these, the general questions, maybe not this chapter, we probably need to go to chapter 8. And then just see if I can figure it out just by looking at it. Mhm.
When you look at the chart, I see that the nitrate was 4 H plus,
Mhm.
was 3 electrons.
Mhm.
And then when you look at like iodide,
Mhm.
there's 2 electrons, and then you
Mhm.
add it to iodine. So is that okay? Like, can you still cancel out the electrons even though there's 3 on one side?
It's not okay. And so this is what you have to do. You have 3 electrons that need to be consumed, but iodide only gives up 2 electrons. And so it's mismatched. When it's mismatched, then we have to adjust the ratios to make it match. Because we're going to be 1 electron short.
Okay.
And so to make it match, then we just do the same thing we did with the ions. So for example, if I double this, then I'll get 4 electrons, but it's still mismatched. And so if I double this, I'll get 6 electrons, but that means I'm 2 electrons short, so I'll triple that. And so if I double the first one and triple the second one, then I'll get 6 electrons consumed, 6 electrons lost. So it's going to end up being 2 nitrates plus 8H plus 6 electrons from the top. And then from the bottom plus 6 iodides. This is going to produce from the top 2 NOs plus 4 H2O. And then on the bottom, we're going to get plus 3 I2s plus 6 electrons. And so the critical step here is that 6 electrons consumed must have 6 electrons produced. The electrons got to cancel. Now it's balanced. Now it works out. And then we just do the same thing. If this is the oxidizer, then this has got to be the conjugate reducer. And so when we go through here, this is the oxidizer, and then the conjugate reducer is this. And if this is the reducer, then this must be its conjugate oxidizer here. The conjugate oxidizer is here. And then we compare the 2 oxidizers, nitrate versus iodine. Which one's stronger? We look at the chart here. Nitrate versus iodine, which one's stronger? Nitrate. And so we're going from stronger oxidizer to weaker oxidizer. And so somebody who says there's no reaction between nitric acid and hydroiodic acid is wrong. It's not an acid reaction, they're right about that. It's a redox reaction. That's what's happening there. And so this is what we do. Then we just clean it up. We clean it up and just say 2 nitrates plus 8H plus 6 iodides yields 2 NO gas. So that would be the NIE that we get from that. Okay. But then, if we know there are only 3 types, then we can stop there because we've already covered the 3 basic types of reactions. We wouldn't have to try to match it with the thousands and thousands of patterns out there, which would be way too much. And so this is why I asked the question, what are the chemical properties of HCl? Do you think in terms of patterns, or do you think in terms of... Yeah, it depends. You try to answer that question using the patterns you learn, single replacement and double replacement, and combination and decomposition, and you're not going to get very far.
For these on the test, is there gonna be partial credit if we like mess up on one part?
Yeah, there's going to be partial credit, so write down as much as you can, so you get credit. The more stuff you write down, the more potential points you can get, even if you can't come up with the final answer.
On the test, you said like the practice exam that you gave us is nothing really, it's not.
Well, it's not going to be exactly the same as your test. On your test, you're going to get more, because we spent so much time on chemical reactions, you know. I decided to spend even more time than I did on, because I tried to stay the schedule, so I spent a lot more time this semester on chemical reactions than last. So you're going to get more chemical reactions there.
So more like free response type of.
Free response, right. What happens when you mix this and this, you know, that kind of thing.
And then really quickly, you remember how we get like for specifically like the PVC with the driving force and like that kind of stuff?
How we get precipitate as a driving force? To get to precipitate, how do you figure out which one's going to precipitate for driving forces? You have to have the solubilities memorized. If you don't have the solubility rules, you can kind of guess, you know, you can take a guess at if it's going to precipitate or not. And what's your guess going to be based on? It'll be based on what we talked about, calcium phosphate versus calcium sulfate. Which one would you guess would more likely precipitate? Calcium phosphate. Calcium phosphate because of the higher charge means greater electrostatic attraction. And the greater electrostatic attraction, the more likely the ions are to come together. And so even if you don't know that particular, you might be able to guess it correctly. It's going to precipitate or not. There are exceptions. I don't know if you know this, the exceptions. You know, we could come up with a rule. The rule is that the higher the charge, the more likely it is to be an insoluble solid. The lower the charge, the more likely it is to be a soluble solid, except for one. Group 1 and ammonium, depends on how much you look at the chart. If you've looked at the solubility chart a lot and it's ingrained in your mind, then you know that group 1 and ammonium all share the same charge, which is +1. And then after a while, after the 1,000th time you've looked at it, you might go, why isn't silver ion included with group 1 and ammonium? Silver is +1. Why is silver left out? These types of questions occur when you look at things a lot. This is why, researchers tend to look at things. And this is why that TED Talk I mentioned, that was just right on, spot on, how you find patterns. You gotta, this is a top 10 TED Talk, and she just threw all the papers on the ground and just kept looking at it. And you don't see these things if you only look at it once. If you look at it once, forget it, you're not gonna see anything. A lot of people, they don't even look at it once. The first time they look at it is during the test, where they're totally confused. And they come up to me and they ask me, does water, you know how many times I've been asked this? People will come up to me and ask me, what's water doing down here? It's the worst. During a test. I thought, oh no. I can't tell them anything. Can't explain because it's something like that. You don't want it to be the first time. So, So the solubility rules, you might start to think, you know, why is silver outside the pattern? It has to do because silver is not a regular group 1. Silver is what we call heavy metal. Those heavy metals are a little bit different as far as the pattern. Another question comes up. Why is lead 2 insoluble but lead 4 soluble? Lead 4 has a higher charge. So why is lead 4 not part of the exceptions? Chlorides, bromides, and iodides are all soluble except for silver, lead 2, and mercury 1. What happened to mercury 2? Isn't mercury 2, shouldn't that be even less soluble than mercury 1, and lead 4 less soluble than lead 2? All these little questions pop up, you know, when you look at this stuff a lot. Problem is like this, you know, you want to look at your scientific, whatever you're working on. If you go, you know, if you go on and are doing some scientific research, you want to look at your stuff a lot because you don't want to be hit with these, you know, questions. You actually would like to have thought about some of these questions beforehand, you know. You might say, oh, good question, never thought of that, you know. That's possible, it's okay, but if there's a lot of those answers like that, then yeah, it's going to require some more thinking. So yeah, you need to know the solubility rules, and we look for patterns so we can guess. Are oxides on the solubility chart? Are oxides on the solubility chart? No. Why not? Oxides are so common. Well, what can you guess? Are oxides more soluble than sulfides or less soluble than sulfides? What would your guess be? My guess would be that oxides are less soluble. Why? Because oxygen is smaller than sulfur. That's why. Even though they both have the same charge, O2 minus versus S2 minus. And we know that sulfides are insoluble except for group 1 and ammonium, so oxides are probably similar. Okay. And so, yeah, you need to know the solubility rules for this. You're going to see chemical reactions again on the final exam, where you're going to get them. All right, if there are more questions, I can stick around and answer those.